Hello, this is Jack Jackson. In this video, we're going to be introducing the derivative function. And we're going to be doing it with the use of a GeoGebra app, GeoGebra activity that I have freely available on the GeoGebra website. So it's called Introducing the Derivative Function number 1. So this is what the app looks like. You can type in the formula for a function that you want here. It graphs it in blue. And you see a point, A, which is an x value, and you can see that point here. You can control it by moving along here, and you can see that the point A, f of A, the corresponding point on the graph, is on the curve of f of x is graphed. You can also move that point by the slider here, or by just typing in a number here, like say 4. Okay, or actually I want to do in, how about -3? Okay, so that gives us a point on the graph. Now, we can also graph the tangent line there. Now, you recall our earlier work that the derivative is the slope of this tangent line. So we're going to look at that. So if you look at that, here is a tangent line segment. And so this little line segment is 1 unit long. And if we go to the right, well, not 1 unit long, 1 unit wide. So if you think of the horizontal change, that's 1 unit, as you can see it here. And it goes basically a half to the left and half to the right. But it goes along the tangent line. So that little black segment is part of the tangent line. And so the derivative then is this vertical distance here. And let me zoom in a bit. Okay, so as we zoom in here, we can see a horizontal distance of 1, and then this is the vertical distance along the tangent line is the amount of the derivative. Here the derivative is positive because as we go to the right, we're going up. And so we can bring that saying that distance down here to the x-axis by clicking on this. These are this one and this one are the same length, and we see that is a distance there. Looks like it's about 2 now, maybe a little bit more. And that is the value of the derivative. Okay. Now the point I want to make is that first of all that derivative is a number. Okay, it is a that number is the slope of that tangent line, but it is a number. Okay, but what happens if I move the a to a different place? Let's say I moved her to -4. Well, now I get a different number for that derivative, a different length here, or now it's getting a shorter length. Over here it's actually even negative. We're going down as we go to the right. Okay, so we can see as that tangent line or tangent line segment is moving, we get different values as we move that point along. But the point is if we, no matter where we place this, we're going to get a particular number out of this, and that is a y value here for this point here I'm graphing is a comma f prime of a. So you only get one output for every input. You're inputting an a and you're outputting f prime of a. Well, that's exactly what we mean by a function. So if we graph this for lots of points, and I can show the trace here as we move this across, and we can graph different points, then we're going to end up getting a graph of the derivative function. Here's the actual derivative function. Now, if you want to turn the trace off, let me show you something. Turn that trace off, and then just move this a little bit, it'll disappear. Okay? And so this is the derivative function, and you can see that as a moves across here, that we get the derivative function graphed out. Now notice, let's go across here where we can see a little bit more of the function. And you can see this graphed along here. So remember, the y values on this red graph, which is the derivative function, are actually the values which are the slopes of these purple tangent lines here. They're tangent to the original function. So notice a positive slope would mean the blue function, the original function, is increasing, and that means that the y value on the derivative is positive. So from about here, somewhere in here, where that crosses the x-axis on the derivative, that's at the minimum right here. From there on out to the right, this function, the original function, is increasing, so the derivative is positive. When we're between this value and this one, between here and here, the original function is decreasing from this local maximum to this local minimum, and that means the derivative is negative in here. The derivative is positive in here because the slopes are positive. From here at that minimum to here at that maximum, the derivative is positive, so the graph is above the x-axis for the derivative. And then this piece on the far left, all the slopes are negative. As we go to the right, the graph is going down, and so that means that the derivative is positive. Notice where the original graph is concave up, here, somewhere in here, right where that maximum is, about here. Then what's happening is that the derivative is increasing. Where the original function is concave down, the derivative is decreasing from here to here. And that maximum and minimum on the derivative corresponds to an inflection point where it changes from concave down to up there, or over here where it changes from concave up to down. Those are inflection points on the original function. And then the original function from there on out to the right, the original function is concave up. So from this minimum onto the right, the original function is increasing. So you can see there's a lot that you can tell about the shape of the derivative and the original function. And again, I can show parts of this as I want. I can show just the tangent line, for example. But once again, remember how the tangent line relates to the value of the derivative, right? It's how much, it's the slope of that tangent line, that is how much the tangent line goes up or down when you go to the right one. Either, well, from that point, right one, or in this case I went both sides of the point, but I'm following the tangent line. So that amount of decrease there is exactly the same as that distance down to the function. And so that application or that activity goes over that. So here's the definition of the derivative at a point. F prime at A is the limit as h goes to 0 of f of a plus h minus f of a over h. Here we're thinking of a as being a constant. The output of this, if that limit exists, is the derivative at that point, which is a number. It's a number with a meaning. It represents the instantaneous rate of change at that point, and it also represents the slope of the tangent line. Okay. The derivative function now, if you look, it's the same thing, but I've just replaced a by x. And on one level you may say, well, I just changed the letter. What difference does that make? Well, it's not just that I'm changing the letter. Up here I'm thinking of a as being a specific constant number that's not changing. Down here I'm letting that a change it be a variable x, and so the output here is not a number but a formula in terms of x that is the formula that goes with this red graph, which is the derivative function. It's a new function derived from the original function. And so now we can talk about the derivative at a point, which is a number, and we can talk about the derivative function, which is a completely new function. So hopefully you can get to GeoGebra and pull this app down for yourself, change the formula, change things around here, examine it, and then take a look at it yourself. And hopefully you found this useful in explaining what the derivative function is.